Hello, I'm Duncan McGladdery, and I developed a Monte Carlo simulation model for financial feasibility analysis. This screen shows the model's variables as well as the model's output. But before I get into the details of this, I'd like to show you what the model is based off. So it's based off a cash flow analysis over a 20-year period. 20 years was chosen because that is the life cycle of both a heat pump and a geyser system. If we look at the cash flow, we can see it's over the 20-year period, and that it is broken up into equipment, maintenance, loan, electricity savings, before tax cash flow, after tax, before tax cash flow in the constant rand domain. We then got depreciation, book value, interest, taxable income, tax, after tax cash flow, and after tax cash flow in the constant rand domain. So converting the cash flow to the constant rand domain is a mechanism to account for inflation. So one thing to note is that this cash flow diagram is dynamic. It's based off the electricity price increase and inflation. And these two values vary every time I press F9. So if I do that, we'll see that these values have changed and that the values in the cash flow analysis also change. And this dynamicness allows us to use a Monte Carlo simulation. So in order to do the Monte Carlo simulation, I developed a data table that has 10,000 entries. And each one of these values is dynamically created and calculates the net present value in the constant rand domain of the project. So if I press F9 again, we'll see that these values are indeed changing. And it is these values that are then used to generate the summary statistics, which can be seen over here. So now we have our model variables. So the first one I'm going to explain is the inflation. And I said that it's normally distributed with an average of 5.56 and a standard deviation of 3.18. In order to come up with these values, I extracted the South Africa's historical inflation data and then plotted it on a chart. So if we look at this chart, we can see that there's not much of a pattern to the inflation. But I then went and plotted it in a histogram. And over here we can see that it follows a normal distribution. We've got quite a nice bowl shape going on over here. I then just used Excel's built-in functions to calculate the average of the distribution as well as the standard deviation. These values are then inserted into the model over here. Then the next thing was to calculate the electricity savings. So this is a key aspect of the model, as it is the thing that we treat as a positive cash flow. In reality, it's not a positive, it's not an income, it's just revenue that is not being spent. So we're considering it's a savings. And this is calculated by taking the previous year's value and multiplying it by the electricity price increase. And linking it to this dynamically changing price increase allows us to account for this variability. So in order to calculate this initial electricity savings, I then went and extracted the price data for the 4 different costs that are associated with electricity, which is energy, network demand, network access, and voltage surcharge. Then plotted these values in this chart. I then needed to calculate the difference in consumption between the geyser system and the heat pump system. That was very easy to do, and they can be seen in this table over here. The next thing was to calculate the savings per category, and that was as simple as taking the price and then multiplying it by the difference in consumption. I then went and calculated the total savings by summing over the 4 different categories. This value over here was inserted into the model just over here as the electricity savings. Now that we have the electricity savings, we need to come up with a way to model the distribution of the electricity price increase. So in order to get the data, I went onto the Eskom's website, and a big surprise is that they are actually pretty good at using Excel. And I managed to get this chart directly from them. And if we look at this chart, we can see that between 2004 and 2008, there wasn't much of an electricity price increase, but we then went into like a super high period where we were being charged from like an increase of between 30 and 35%. This then kind of stabilized in 2013, and it's looking like it's kind of hovering at around like 7 to 10%. So in order to model this distribution, I thought since there's doubt, let me just plot it in a histogram. And if we look at this, we can see that it kind of follows a normal distribution. I think it's a fairly weak assumption, but it's probably the best assumption that I can make. And then again, I calculated the average and then the standard deviation. So that's how I came up with these values of 14.54 and 12.33. However, I don't believe that this is going to be a true reflection of what's going to happen in the future. And the main reason for that is that I feel that this period really skewed the results. So I'm going to assume that the price of electricity is going to be closer aligned with that of inflation. And there are two reasons for that. One is that that period, this period over here, kind of skews the results. And we also haven't had much load shedding in the past few years, and there's a chance that we might develop a new nuclear power station. So I don't think that the price is going to increase too much. So I changed those values. Then the last thing to do is to come up with the MAR. So I selected the MAR value to be 17%, and this was done through looking at the holding company's return on investment over the last 5 years, which was 11.81%, then looking at the interest on the loan, and then looking at inflation. I then went and selected the largest value of these and added a risk buffer of 5 to that and came up with a MAR value of 17. So now we have the model and we can use it for experiments. So I'm going to press F9 and it's going to update the model. So over here we can see the distribution of the net present values. And if we look at our summary statistics, we can see that on 96.8% of the time, it resulted in a positive NPV, which suggests that we should undertake the project, and that the average value of the NPV was 2.7 million, which is quite a nice high number. Now, part of this project was to evaluate the effects of two different loan schemes. So in this model, I used a loan repayment of 20 years, and then I copied this model but changed the loan repayment period to 5 years. And if we use the same input values and run the simulation, we can see that in this case, the project is profitable on 90% of the occasions, and that the average value is 2.26 million, both of which is lower than using the 20-year loan repayment scheme. So this leads me to believe that we should take a loan out for 20 years. So a further requirement was to evaluate the effect of varying MAR. So I chose 17, but there's a chance that the managers believe that that this project is riskier than what I perceive it to be. So they might say increase it to 25. And we can see what the effect of this is by pressing F9. And then, well, we can see that the percent of the time it's positive drops down to 75%, and that the average value is only 874,000. So changing the MAR value had quite a large effect on the attractiveness of this project. And the reason for that is best explained if we look at this cash flow if we look at this project's cash flow. So over here we can see that this project requires an initial large capital outlay, and then there are a whole bunch of benefits that come in as time goes on. But now the larger the value of the MAR, the less the benefit of the cash flows that happen at a later period of time, as it places a lot more emphasis on having money in your pocket now. So that is why having a higher MAR value reduced the attractiveness of this project. So for interest's sake, let's increase this MAR value to 35 and see what the effect is going to be. And then we can see it drops down to only being positive 28% of the time, and the average value is minus 280. But realistically, no company is going to have a MAR of 35%. They're going to be Mark Zuckerberg if they can expect returns like that. So, in conclusion, I believe that the heat pump system is the preferred choice. Thank you very much for listening, and enjoy your holiday.